So we will now discuss a physical picture which tries to explain a little bit better the behavior of the Carnot spiral. So to understand the Carnot spiral, we're going to look at example of a line source. And the line source, as we know, emanates a cylindrical wavefront. And we want to now divide this line source, the wavefront from the line source, which is cylindrical, into the Fresnel half zones. And so we do that as the same way. We now draw cylinders of radius r0, r0 plus lambda over 2, r0 plus lambda, and they will intersect the primary wavefront at these points over here. So for example, at O, at Z1 and Z2 on those strips that you see here. So each of these strips, again, is out of phase with the previous one by pi. And the contribution from each of these Fresnel half zones is proportional again to the area of these half zones. But as you can see, the area of the half zones decreases rapidly as we go away from the center. And the reason for that is because in the cylindrical case, which is different from the circular case, the radii of the circular zones increases, thereby keeping the area roughly constant. The radii increases, therefore keeping the area constant. If I now divide up each of these subzones, so for example, if I took a smaller zone within this just as I did with the cylindrical, if I divide this up into n strips, n little strips that go across like that, and each of these n little strips is now going to contribute a phasor, which is shown here on the right hand side. And again, the phasor is going to be less as it as it changes its angle because of the obliquity factor, and it's going to get smaller much quicker than in the case of the spherical or circular zones. And so you see that instead of the vibration curve closing back almost on itself in the circle or mostly following a circular pattern, this one is going to spiral in much more quickly than in the spherical case. And so that is the polygon or the smooth version of that vibration curve that you're seeing there will be the Carnot spiral that I'm showing here. This is, of course, just a sort of physical picture, not a mathematical proof. But we can also see this indication of this in the Carnot spiral quite well, because as you may remember, the angle that the Carnot spiral makes, the tangent to that, is given by pi w squared over 2. And so when we come to the first Fresnel half zone, which is ZS1, corresponding to the point Z1 here, we know that phasor has to be pointing exactly at 180 degrees, which means that the angle that it makes with respect to the axis must be pi, which gives us that w squared is equal to 2, or w equals root 2, which in fact in the Carnot spiral, if you go back just a bit, and I'll show you that, is exactly the point root 2 over here, which corresponds to that angle. And so this kind of helps us to understand what is going on with the Carnot spiral over here. Okay, and so similarly then we can go back, we twist one more time and we come to ZS2, which corresponds to the point Z2 here, and that is again now facing back and has a phasor. It's gone through a full rotation of 2 pi. And so in fact we can compare these values with the values on the Carnot spiral and see that they line up quite well. So with that in mind, we can now do the Carnot spiral. We can use the Carnot spiral for the single slit to predict the irradiance pattern. So here I'm saying that I'm setting y1 and y2 to minus infinity and plus infinity. So the contribution to the phasor, we need to square the phasors and or find the magnitude squared of the phasors for both the u and the v variables. And the u variable is therefore going to get fixed. It's just going to be square root of 2. Okay. And the v variable, which is the one that we need to calculate, which is along the z direction. Okay. And so again, we use the same technique. We stretch a piece of rope or string, whatever you want to call it, from the point, let's say in this case that again we're starting with -1 and +1 for the z direction, and therefore or the v direction. And as we now move our point of observation down towards the geometric shadow, we see that the point is going to get less negative. So it's going to move up to this point over here on the z direction. Z1 is going to get less negative, and Z2 is going to get more negative. And so we see that the string now has to stretch up in this extra region over here, keeping the length of the string the same, will reach around to there, and that's why the phasor now has a shorter distance. This is just like the rectangle. Having discussed how the pattern from the single slit looks as we move into the geometric shadow, we also want to look at what happens when we just increase the size of the slit. And so here we are plotting the irradiance pattern by changing delta W. Remember, delta W or delta V or delta U gives you the length of the slit in the normalized coordinates. And so, or in this case, the width of the slit. And we are plotting this as on a coordinate where W1 plus W2 over 2 is always centered around the 0 of the slit. And we can see then that because of the way this phasor is drawn here, you'll see that we reach a point when delta W is equal to 3.5, and the string spirals all the way around to here. We'll reach this point where any subsequent movement of increase of the width of the slit can only result in increasing the length of this chord, because the length of the chord is sort of a minimum right between these 2 points over here. And therefore, any further changes on either side of this will make the intensity go up. And therefore, we again verify that there can indeed be interference fringes within the central shadow region, or in this case, shadow is the wrong word, but the bright region of the slit can also have interference fringes. And again, this can be verified in many different cases. Here, this is just plots of for delta W equal to 5 now. So you can see a lot more fringes. In fact, this pattern is starting to approach. And here, next to each of these, the gray vertical line represents the Cornu spiral for that particular position in the irradiance distribution. We see that as we move this outward, this chord increases or decreases in length, corresponding to a maxima or minima in the intensity. And finally, it's going to start reaching the geometrical shadow region, as you can see here. And then the intensity is just going to gently decrease with maybe 1 or 2 smaller ripples out here. And this is for large slit width over here. And the ultimate limiting case of this is, of course, when the slit is moved completely to infinity. That would be what we call a knife edge, because we only have the one slit on one side and the other edge of the other slit has gone off to infinity. And that is the knife edge or semi-infinite screen. And as we can see also, as we'll see in the next slide or so, that the pattern that we are starting to approach here on either side, this is going to look like a superposition of 2 knife edge patterns. So a knife edge on the left-hand side and a knife edge on the right-hand side. And they don't really worry so much about the fact that there is another slit somewhere away, because it's starting to look like an infinite distance away from that first knife edge. So here's an example of the knife edge. So let's start with the point 3. The point 3 is directly opposite the knife edge or the semi-infinite screen, the edge of that screen. And of course, on the other direction, in this case, y1 and y2 are both infinite, or minus infinity and plus infinity. And here only z1 is finite and z2 has gone off to plus infinity. Because z2 has gone off to plus infinity, the phasor will always end at this point over here, right here. So all the phasors will always end on this point in the Cornu spiral, as we can see. And because of that, all we have to do is trace out what happens So at the point 3 is exactly opposite the center. That is the origin of our coordinate system in this Fresnel, in the Carnot spirals. And if we move down further into the geometric shadow, then again Z1 gets positive, or in this case Z1 corresponds to a normalized coordinate V1, and at the position 2, for example, that coordinate will be somewhere here. At some even deeper down into the geometric shadow, the Z1 is even more positive, and therefore it becomes closer to the infinite, and you can see the size of these phasors is getting smaller and smaller. Whereas if you go in the other direction, going upward, then we can see that the size of the phasors gets larger. So, and then the maximum value that it's at is at this point 4, where it can reach about 1.4, which you can see that is the farthest that the phasor can be away from this endpoint over here. And so that will be a very high maximum, and then it'll start to undergo some oscillations, and then it'll reach a minimum over here, and then undergo some more oscillations, for example. So that is what we expect from the knife edge or semi-infinite pattern, and that is indeed what we see. So you can see here the edge over here, the point 3 corresponds to a quarter, which you can see here as well. This point is going to be exactly 1/4 of that distance, and the maximum value over here, again given by the square of that phasor, and then minimum at the point 5 that I just talked about, and the points 1 and 2 are in the geometric shadow region, as shown here. And here are some pictures and a graph of the knife edge. With modern devices, we can resolve hundreds of these fringes with lasers and scanning detectors and so on. So having talked about diffraction from a slit, I want to now talk about the complementary situation. Just like when we did the circular aperture, we talked about the circular obstacle, and we saw that they were sort of complementary to each other. Similarly, we have done the slit. So the complementary situation to a slit is now a narrow wire, for example. So here is the Fresnel diffraction patterns from 3 different narrow wires. The first one is just a piece of pencil lead and illuminated by, I think, a bright laser again. And then the next one is a 1/4-inch diameter metal rod. And then the last one is electrons, which are doing Fresnel diffraction off of a 20-micron quartz filament wire. So you can see all these cases have very similar diffraction patterns, which is the Fresnel diffraction that's occurring. And now, of course, our values for U1 and U2 are basically going to go from U2 up to infinity. So, right, I mean, we can go on either side to infinity, or minus infinity and plus infinity. So we have to integrate from minus infinity to U2, or U1, sorry, up here. So the piece of string will basically stretch from here up to this point over here. And then similarly will stretch from here up to this point, or stretch from U2 up to this point over here. And so these two integrals, as we can see, there are always going to be some situations where this is non-zero in the center, and therefore we can expect to see this sort of bright line here. These two are never, so of course we have to vector sum these two phasors, but given how they're pointing, you can clearly see that these phasors will never cancel each other out. So there's always going to be some bright region right here in the center. And so that is one of the things that you expect to see with Fresnel diffraction from a narrow wire. Which brings us to Babinet's principle. Babinet's principle states that 2 diffracting screens are complementary when transparent regions of one are blocked by the other and vice versa. I mean, that's just the definition of complementary diffracting screens. So if E1 and E2 are fields from the apertures in the screens, when the 2 apertures are simultaneously placed on top of each other, because the transparent region of one is blocked by, the apertures, basically, then there are no opaque regions, right? basically the two apertures in the two situations are being placed on top of each other. And so wherever previously there was light being blocked is now we're allowing light to go through. So if there are no opaque regions, then E1 plus E2 is equal to EU being the total wavefront. And if EU equal to 0, then we see that E1 must be equal to minus E2, and the irradiance patterns are identical. Now, normally for unobstructed waves, there are no zero amplitude points. Usually there's always some place where the amplitude is non-zero. However, as I'll just show you in a second, in Fraunhofer diffraction, this often arises, this kind of situation. But before I talk about that, let's just take a look at Babinet's principle in the Fresnel diffraction case, because the same principle applies no matter which situation it is. E1 plus E2 must be equal to EU. So here I'm drawing a situation which is the situation of a slit and the wire, and we see that the two going from here to B1, which is the wire, and then from here up to B2, that is the slit. The sum of these two is always going to add up to the unobstructed wavefront over here. So the phasor from here to here plus there to there will always add up to give me the total phasor, which is over here. Okay, so that clearly demonstrates this principle, and in the same way we can show this on the vibration curve for any Fresnel zone. This is the aperture that we already kind of saw this in the diffraction from circular apertures. When the vibration goes to the circular aperture, and then if it goes through a circular obstacle, then it has to go from here out to infinity. And so you can see again the sum of these two adds up to the unobstructed wavefront. So in the case of Fraunhofer diffraction, normally if we didn't have any slit in place, then we know that this is the setup. We'll have a source which is being imaged by these two lenses onto the screen. So you can see that the unobstructed wavefront has zeros all over the screen except for the very central region. So Babinet's principle then assures us that complementary apertures, if they are placed in this Fraunhofer diffraction pattern, will give us the same irradiance pattern on the. And this is a demonstration of the Babinet's principle in Fraunhofer diffraction. So we have two types of apertures. The one on the top has holes in certain regions which are in a plus shape, and those holes in this opaque screen give rise to the diffraction pattern that you see on the right hand side. And on the bottom we have a situation where we have a transparent plate with plus signs marked on it, and then we also get the identical diffraction pattern on the right hand side. So to summarize for week 11, what we have learned, we have focused on Fresnel diffraction. We covered the obliquity factor and for spherical wave propagation, which led to the modification of the Huygens-Fresnel principle. And we used that to do the Fresnel zone construction and derive vibration curves for the circular situation. And that allowed us to then understand what happens with circular apertures and obstacles. We covered the Fresnel zone plate, which can be used to make lenses in many different situations where it's difficult to find lenses materials. And we then discussed rectangular apertures and the Fresnel integrals. When we have no cylindrical or spherical symmetry, we use the Fresnel integrals to calculate the situation and the irradiance pattern, and that brought us to the Cornu spiral, which is a beautiful geometric way of representing the results of the Fresnel integrals and allows us to predict intensity distributions from various types of geometries, such as the slit, the knife edge, the obstacle, the wire, and so on. And that finally also allowed us to conclude that Babinet's principle, which allows us to predict the diffraction patterns from complementary types of diffracting screens.